Be like over here. Gravity is off, right? Everything sort of floats, right? Okay. Then if we floated to the middle of the room, so maybe we push off the floor or something like that, right? And we found ourselves in the middle of the room, and I am sitting there, and you're sitting opposite me. And if I give you a push that way, you will go that way, but there's no way for me, while floating in the air like that, right? There's no way for me not to go this way. There's no way for me to push you that way without me getting pushed this way. These are equal and opposite reactions. So let's draw a little picture here, right? Okay? That person's pushing this person this way, right? If this person pushes that person that way, there's no way for this person not to go this way. Yeah? So let me just ask you, what makes a car go down the road? Okay, yeah, tires push on the ground, and the ground does what? Yeah, pushes back. I push on the board actually pushes back. I know it pushes back on me because I see my hand flatten out. I feel the force on my hand, right? Okay, so reaction forces actually act on different objects, okay? Now, here's this little truck here, and Mr. Duggan, I told Mr. Duggan to go get me a new car. So he gets me this. It's way too complicated, right? But I wanted to replace that. Remember that thing we used for boat crossing river demos? It's like on its last leg. So this was what Duggan comes back with, right? Duggan always gets like, fancy stuff, right? Check this out. It's like, here, let's start the motor. Remote control, right? Let's go forward. Whoa. It keeps going for a while, It's like, stop going forward. Good. All right. It also responds to voice commands. Okay. Now let's stop the motor. Let's lock it. And it used to have an alarm, like if you picked it up and dropped it, it would go wah, 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 but it's like, I think Duggan dropped it enough that it doesn't do that anymore. So let's unlock it. All right. Let's honk the horn. See, now, you guys have gotten about as much enjoyment. Can you put your phone away, please? Or I will smash it. Thank you. All right. Should we go to that rule? I want to be relaxed about it, but I can go to I will confiscate your phone if we need to. Okay. All right. So now what we're going to do here is we're going to put this. We're going to put this on a road because we've got a road. Don't we have a road? We need a road, right? So here we've got a road. And we've got this thing. And the question is, and I like this. This is beautiful because I can make it start going. I can make it start going without touching it. I don't have to turn a switch. Yeah? This is a very good thing. So here we go. Are you ready? What's going to happen when I hit forward? That's kind of fun, huh? Like, whoa. Yeah. How come the road did not push the car down the road? Why didn't this work? Which has more mass, this or this? Yeah, this has way more mass. Normally it's the other way around, right? The road is attached to the earth has way more mass, right? So when we push on the earth pushes back and the earth wins. Okay. Here we had an example of a very lightweight road, right? Okay. Yeah, so there we have it. How about more examples of the third law? The third law, how about has anybody ever fired like a pistol or a rifle or a shotgun? Yeah, what happens? The bullet goes that way and the gun goes the other way, right? How about rockets? What do rockets push off of in space where there's no air? Airplanes can push through the air. A propeller airplane can kind of screw its way through the air, yes? Okay, right? And ships can push off the water, but in space there's nothing there, correct? So what are they pushing off of? Yeah.
They burn their fuel, and that creates stuff behind it that's pushing it forward.
Exactly right. Yeah. So an airplane does this, or a rocket ship does this, right? It's got projectiles, right? And it takes these molecules and through an explosion. I was about to throw this that way very rigorously, right? Through some explosion, it propels them that way, right? Every time you shoot something that way, you recoil this way, right? And of course, if you're doing this at, Mach 3 or something like that, just a small amount of fuel going that way at Mach 3 is going to push you this way at some speed. What happens when you run out of fuel? Yeah, you're all done. Whatever your velocity is, it won't change, right? Okay. So what they talk about with rockets, they talk about something called delta V, a space probe. The delta V is the biggest change in velocity where'd my hacky say? Oh, it went under there. Okay. The delta V is the biggest change in velocity that a space probe can undergo in deep space. Now, if you think about it, it's sort of an interesting thing, because the more mass you put on the ship to burn, the harder it is to speed up your ship. So putting more mass on isn't necessarily the best thing, is it? Right? The best thing is to speed the stuff up to an incredibly high velocity before you release it. So the very best engines we have are things called ion drives. Yeah? And what they do is they speed stuff up to like tens of thousands of kilometers per second. Right? Xenon atoms is what they do. Charged xenon atoms. They hurl them out into space. Right? Xenon because it's heavy. Right? They hurl them off into space, and those engines exert a force in all of their technical prowess equal to the weight of a sheet of paper. Why does that work? It doesn't work, by the way, to lift off from Earth. You need more force than that. Why does it work in deep space? There's no other force. There's no friction. There's no air friction. The force that engine's exerting is the only force on it. And since it's the only outside force, it's unbalanced and therefore causes an acceleration, right? These take a long time, right? So if you put an ion drive in orbit around the Earth above the atmosphere, it'll take a long time for it to ramp the thing up until it can escape from the atmosphere. But the cool thing about ion drives is that they can be solar powered. Huh? That's cool, because they're electric. They run on electricity. Yeah, they need like xenon or something like that. So when they run out of that, then they're done, right? Okay, so this is the deal. The force here is our force in newtons. It is called the net force, the unbalanced force. Okay, if for example we had an object and we had 5 newtons this way and 2 newtons this way, 5 wouldn't be the unbalanced force and 2 wouldn't be the unbalanced force. The unbalanced force would be, yeah, let's point your eyes up here. Yeah, the unbalanced force would be the difference between 5 and 2. You'd have an unbalanced force of 3 newtons this way, right? So if there's more than one force, you've got to...
Can you do the survey by the end of the day?
This one?
Yeah.
Are you talking about me personally?
Yeah.
Yeah, sure.
I have you next, so...
Yeah. So that's what we're talking about. And at first we're just going to deal with that, and then we'll deal with what happens when there's more than one force, right? Mass is in kilograms. Let me get a kilogram and we can pass that around. And I had one up here. But I think it is migrated. It is migrated. It is migrated to the back of the room. All right. This is a kilogram. This is not Le Grand K. Okay, Le Grand K is like the actual kilogram made of platinum in Paris that defines all other kilograms. It is taken out of its case every year and compared to several deputy platinum kilograms. Why platinum? Because platinum doesn't react with air. If this oxidizes, it changes its mass. Le Grand K, the actual kilogram that defines all other kilograms, is really still a bar of platinum. Okay, this is not that kilogram. This is probably 1 kilogram plus or minus 5%. I don't know. It had a little thing on the top that's broken off. So we can pass this around. What you can do is you can put it on your hand and say, I feel the force of gravity on it. Right? You can also take it like this. Don't do this at your neighbor. And go, I feel its resistance to a change in motion. That is its inertia. If you were to go into outer space, it wouldn't push your hand down. But if you tried to go like this, shaker weight style or whatever, right? Okay, it would still resist the back and forth. It would still resist that, but it just wouldn't pull your hand down. We could pass that around. That's a kilogram. Okay. On Earth, this weighs 2.2 newtons. In space, it weighs nothing. It always has a mass of a kilogram. So mass and weight aren't the same thing in physics. And then acceleration, just when you thought we were going to be done with our linear kinematics formulas, oh no, you can get acceleration with this one, with that one, with this one, with this one. So you have to be able to at least solve those for acceleration. So sometimes, instead of just telling you what the acceleration is, you've got to solve for it first, then, yeah, you know. So this is, use any formula for acceleration.